Hello, my name is Lyle Schemmerling, and with the help of Rakesh and Deepak, we are going to talk to you today about the Google Protocol Buffer. What you will find in this presentation is that we are going to do a quick overview of what the Google Protocol Buffer is, an intro into what it is and where it came from, a quick overview of data serialization, the history of the protocol buffer, typical model operation in using the protocol buffer, how the Google Protocol Buffer compares with other formats, namely versus XML, quick sample snippet into using a protocol buffer versus some XML, some analysis on that, then comparing the protocol buffer with JSON, and some performance statistics as well. Okay, so the Google Protocol Buffer, what it is it was designed in 2001, a proprietary format to Google, and later in 2008 became an open source thing that everybody can start to use. This is a battle tested, it's very stable, it's a very well trusted method for data transfer and serialization. And every time we hit a Google page, we're going to see several services and data that are delivered using the Google Protocol Buffers. And it's basically the glue that holds all of Google's services together today. Official supported languages for the protocol buffer are C++, and Java, Python, and JavaScript, which, while it's not an extensive list of languages, gives a pretty wide user base in people who can take advantage of the protocol buffer today. And it does have a lot of third-party support for other languages of variable quality. I do know that they have .NET variants of the protocol buffer as well as many other languages. Alright, so the Google Protocol Buffer is also commonly called the ProtoBuff for short. And it's a Google language-neutral, platform-neutral, extensible mechanism for serializing structured data for use in communication protocols, data storage, and other transfers across the web. They're flexible, they are efficient, and automated mechanism for serializing structured data. You can sort of think about them a lot like you'd see XML or JSON used to transfer data across the wire. You can define a lot of the data inside of a protocol buffer file called the proto-C file, and then compile it against a variety of languages to generate classes that can access them. Protocol buffers are also backwards and forwards compatible, so you can change the data structure and not break functionality in classes that are already compiled against the old protocol buffer format. This is a huge deal because intercompatibility can be a big thing for upgrading any data structures that you have. A quick overview, kind of how the protocol buffer works. It's a little bit of a hard to follow diagram, but the main thing here is that you have the activity on the left, somebody who's going to build up the protocol buffer and send it across. And then you have the activity on the right, which is someone who's going to consume the protocol buffer. And you see basically what happens is that it's compiled down into a byte array, which can then be parsed on the other side. The byte array gives you a lot of advantages, which we'll talk about here in a little bit. You also need to kind of know the class model, and the right-hand side is the activity too in order to parse that. So basically both sides need to know what the protocol buffer is supposed to look like, and then they can tear apart the byte. So quickly, let's talk about data serialization. It's interaction between any two web services, applications, or APIs. It's the most critical part of any web application. These interactions are the forms of data streams sent across different applications. One such concept of data sharing is coined as data serialization. Serialization refers to encoding the data in a serial pattern. Extracting one part of the serialized data structure requires that the entire object be read from start to end and then reconstructed. And in many applications, this is the linearity here is an asset because it enables a simple, common I/O that can be utilized to hold and pass the state of an object. There are many data serialization techniques that are available today. Most popular are JSON and XML. Today we are going to be talking about a new technique, the protocol buffer, which we've kind of already introduced, but basically is an improvement on those previous formats. So why did Google decide to build a protocol buffer? Well, they had encountered some problems in their own sort of servers and how they communicated with each other. They were using what was actually called a protocol buffer class, and they ended up sort of generating multiple versions of this class, and they wanted to transfer data across between servers inside of Google. And what you see here is a quick snippet of what I believe is Java code, where they are checking the versions of what protocol buffer was coming across in an if-then tree, and then having completely separate sets of code to handle the different protocol buffer implementation. These changes were difficult to make system-wide. There was a large risk of breaking functionality when changing what was inside of those protocols, and there were language-specific ways of handling the protocol that could mean that data was handled differently or incorrectly. So they decided to generate the protocol buffer, which solved all of these problems for Google and had some handy side effects as well. The format works well when persisting data, for example. Alright, so how do you use a protocol buffer? It includes writing down a bunch of struct-like messages formatted in an IDL language. And then you're going to run a tool, the protocol buffer compiler, and it will basically, for the languages that you specify, output classes that can access, parse, set, create, build all of the protocol buffers. And they have compilers for Java and C++, RPC interfaces, composite type extensions, and data versioning. Some of the projects include Google, ActiveMQ, which is a cloud-based messaging service, and Netty, which is an RPC service as well. All of those use protocol buffers to help store and send messages around. Alright, and let's compare protocol buffers versus XML. They are the driving force behind, the driving force behind using protocol buffer over XML is that it is a simple and human-readable structure and lightweight on overall memory consumption. Protocol buffers, when in use, tend to be 3 to 10 times smaller data-wise than XML. And can be 20 to 100 times faster, so a lot more efficient than using XML to transfer data around. They're also a little bit less ambiguous, and can generate classes that are easily programmable. So like I said before, you can generate a Java class that will allow you to sort of manipulate and handle a protocol buffer. However, the protocol buffers cannot be manipulated in native form in a file by humans, and that's due to the fact that it compiles down to a byte array, whereas XML is, we're used to looking at, similar to HTML pages. You can go in and see the tags and edit them and move them around and stuff, and you do need to have a program that knows how to handle the protocol buffer and pull it apart in order for you to actually be able to read it. So here's a sample snippet comparing the two. This is an XML snippet. As you can see, it's got tags, inside of the person. Then you're going to have the person's name and the person's email. It's fairly straightforward and human readable. But again, it's highly inefficient for moving across the wire. Looking at the protocol buffer, now granted, this is the string representation, so it's not quite the compiled byte array that gets sent across the wire, but in terms of the data and how it's structured, it's very, very similar and easy to read. It looks almost exactly the same logistically. So if you look at it, the Google protocol buffer is easy to read. It's, again, sort of only rendered in that textual format for reading and debugging, and it's put into that byte array when it's sent across the wire. So those two snippets, that XML snippet that we were looking at was 70 bytes long, and the protocol buffer snippet, which contained the same data, was only 28 bytes long. The XML snippet would take 5,000 to 10,000 nanoseconds to parse, whereas that protocol buffer would only take 100 to 200 nanoseconds to parse. So in terms of data transfer efficiency, again, a lot of gains to be made. So another really popular format for transferring data around is JSON. which is already a whole lot better than XML, but it still comes with a significant overhead. So we've got a quick piece of sample JSON code in there. Again, that looks really similar to the protocol buffer. It's got key value pairs. And in this example, that type ping time, integer, there is a 32-byte large piece of code that it apparently has 71% redundant data in the byte structure that it uses. And if you used a protocol buffer with the same information, you get one that comes out to be just about 7 bytes long, while still being able to distinguish between the two messages in different types. They're a whole lot faster than JSON due to the size of the object, because it's compressed down to that byte array. And protocol buffers are also backwards and forwards compatible. So again, you can add new fields into the protocol buffer, and old code doesn't care, and new code can use it and doesn't care if necessarily the old ones disappear. It doesn't mean that applications expecting the data won't break, but in terms of actually using the protocol buffer, it will be okay. And part of that is due to the fact that protocol buffers provide a schema, which is that proto-C file, and allows both the creator and consumer to know how that protocol buffer is structured. One downside is that JSON is more widely used in the protocol buffer right now. Because protocol buffers are much newer and they're proprietary to Google, JSON has a much wider adoption, and it will be more familiar to developers who are familiar with working with web protocols. So a couple of other statistics here on protocol buffer performance. There's a bunch of different JSON formats in here that you can see. We said it's been around for a long time. The main thing to take away here is that at the very bottom of the list is the protocol buffer, which is much faster than all of those. And I think this particular statistic is referencing that protocolbuffer.net framework, which I had mentioned earlier in the slides. And some other stuff to show you here, just comparing to common formats and sort of the advantages you get when using a Google protocol buffer. They are always splittable. You can split them up. They're very efficient when you're parsing. You can reuse protocol buffers over and over again. You can add new fields to them. You can ignore the unused ones. They're small in data size, and they definitely have a hierarchy, which, when compared to any of those other formats, none of them hit all the same marks. And just some more stats for you. Again, you can compress them down. Their uncompressed size can go down to compressed size in about a ratio of 2.03. And then the average time in milliseconds to deserialize them. Minimum's 880, which again is the high number, and max in terms of speed would be 861. So they're pretty consistent and efficient. And that's all of our references. Thank you very much. And if you come across the topic of which data transfer protocol to use in your upcoming careers, take a look at protocol buffers. They're pretty cool. Thanks a lot.